Hello friends, welcome to my series on questions from different aspects of machine learning. In today's video, I am going to discuss a question which is related to the concept of IID or independent and identically distributed. This is an important concept in ML and its solid understanding is necessary to appreciate the different statistical properties and assumptions of our learning algorithms. Let us move to the question. We first define the setting of the problem. Suppose I have a fair coin such that probability of obtaining heads is 0.5. Now I perform multiple tosses of the coin and observe whether ith toss resulted in a head or a tail. With the ith toss, I associate a random variable x sub I such that it is 1 when we observe a heads and 0 when we observe a tail. Under the setting described, let us ask three questions. Question number 1. Is the sequence of x sub I IID? Question 2. If the underlying coin is not fair, is the resulting sequence of xi IID? Note that this question differs from the question number 1 because in question number 1 we made an assumption of the coin being fair. Question 3. Assume that we define another random variable a sub I, which is sum of xj for j equals to 1 to I, or number of heads in the I tosses of coin. Is the sequence of a sub I IID? To answer the question, we need to understand a little background. Let us try to understand what it means by IID. IID is an acronym for independent and identically distributed. Let us try to develop an intuitive understanding of what it means by independence and identically distributed. The concept of independence arises when we are talking of more than one event. Intuitively, for two events A and B, if the probability of B remains unchanged irrespective of whether A has happened or not, then the two events are said to be independent. Consider a fair coin such that the probability of heads is 0.5. We perform 4 coin tosses resulting in a sequence head, tail, tail, and another tail. It must be obvious that despite of observing tails in the second and third tosses, the probability of head is still 0.5 in the fourth toss. So, observing a whole sequence of tails does not imply that the probability of heads will increase in the subsequent toss. Let us look at another sequence of 4 tosses resulting in 4 heads. Even after 4 heads, the probability of obtaining a head in the 5th toss is still 0.5. This clearly means that the probability of observing a heads on the 5th trial stays constant irrespective of what we observe on the first 4 tosses of the coin. Let us consider a third sequence where we are seeing an alternative heads and tails. So what it implies is that the probability of observing heads in the subsequent trials continues to stay the same. Now let us move to the concept of identically distributed. Intuitively, it means that when we are performing multiple tosses, the probability distribution on every toss stays the same. To better understand the concept and to distinguish it from independence, consider a fair coin. Let us perform 4 tosses with the same coin and assume that we obtain a sequence of heads followed by 3 tails as shown in the video. It must be clear that every toss is independent of the previous toss as we discussed before, and that the probability of obtaining heads or probability distribution is same across the multiple tosses. Consider Another example with the same coin. This time we obtain alternating sequence of heads and tails. What is important to observe is that probability distribution stays constant for every toss. To better appreciate the concept, let us consider another setup. Here we have a fair coin like we discussed before, and we performed 4 tosses with the coin. We obtain a sequence of heads followed by 3 tails. To contrast it, let's have another setup where we use different coins, each having different probability of heads associated with it, and toss them to obtain a sequence of head and 3 tails. Note that although we obtain the same sequence, the probability distribution changes for each toss. The first toss was done with a coin that will always show heads, and the fourth one with a coin that will always show tails. So, in the first setup, tosses are identically distributed. In the second setup, they are not. With this understanding, we are equipped to address our question. So let us move back to our questions. The first question that we were asked was, is the sequence of x sub I IID? Let us consider an outcome sequence associated with 4 tosses of a fair coin. Here x1 is 1 as we obtained in heads, and x2 is 0 because we obtained a tails. Similarly, x sub 3 and x sub 4 are both zeros because we obtain a tail. Clearly, we have seen how a sequence of fair coin tosses are independent because the probability of heads on an ith toss is not affected by what we observe in the previous tosses. Since the value of xi is completely determined by what we observe on the ith toss, and as the ith toss is independent of what happened in the previous toss, hence x sub I is independent and of random variables x sub 1 to x sub I minus 1. We also observe that the probability distribution was the same for every toss, and hence x sub I are identically distributed. Now let's move on to the next question. If the underlying coin is not fair, is the sequence of x sub I IID? Clearly, the only implication of the fact that coin is not fair is that probability distribution is different. The coin tosses are still independent, and due to same probability distribution, they are identically distributed. Moving to the third question. Assume that we define another random variable a sub I, which is sum of all xj's from j equals to 1 to I, is the sequence of AI IID. The first step is to study the sample space for AI. Since a sub I is equivalent to counting the number of heads in the I trials, the sample space corresponding to a sub I is a set of non-negative numbers between 0 and I. To better understand this, let us consider the probability distribution of a sub 2. We have a probability of 0.25, 0.5 and 0.25 for observing 0, 1 and 2 heads respectively in 2 tosses of a coin. This is because there are 4 different possible outcomes. One among them has a 0 heads or 2 tails. 2 of the outcomes have 1 heads each, and 1 outcome has 2 heads. Thus, we can understand the probability distribution for a sub 2. Let us consider the case of a sub 3 or 3 coin tosses. This has different sample space, and the probability of obtaining 0, 1, 2 and 3 heads is 0.125, 0.375, 0.375 and 0.125 respectively. This is because we have 8 possible outcomes as shown. We can rearrange the possible outcomes to realize that one outcome had no heads, 3 outcomes had 1 head, 3 outcomes have 2 heads, and 1 outcome have 3 heads, and hence the probability distribution. So what we observe that the sample spaces for A sub 2 and A sub 3 and A sub 4 are different, and hence the probability distributions are also different. Thus, it is pretty clear that the sequence of A sub I cannot be identically distributed. Now, let us address the question of independence. To understand it, we consider the case of A sub 2. As we discussed before, the probability distribution of A sub 2 has a probability of 0.25, 0.5 and 0.25 of observing 0, 1 and 2 heads respectively in 2 tosses. Suppose that we toss the coin once and observe a head. Now the conditional probability distribution of A2 changes because there is no way A2 can have 0 heads, as we have already observed a head on first toss. So the valid values of A2 can have is 1 or 2, and they are equally likely, conditional on the fact that first toss results in a head. Consider the other outcome where the first toss results in a tails. Now A2 cannot have a value of 2, as we already have observed 1 tails in the first toss, and hence the valid values are 0 and 1, both being equally likely. Thus we realize that prior probability distribution of A2 changes based on what we observe in the first toss of the coin. Clearly, A2 is dependent on the value of x sub 1 and hence the value of A sub 1. Clearly, sequence of A sub I are neither independent nor identically distributed. To summarize, sequence of xi is IID when the coin is fair as well as when the coins are not fair. The sequence of A sub I, where A sub I is a sum of x sub 1 to x sub I, is not IID. Thank you so much for viewing the video. I hope the video explained you the concept of IID. If you wish to be updated with my other videos, please subscribe to the channel.